All right, let's go through some related rate problems.
Take a look at problem number 7. Problem number 7. You have a spherical ball is increasing at a radius of the ball is increasing at a rate of 2 centimeters per minute. At what rate is the surface area of the ball increasing when the radius is 8 centimeters? Okay, so we are saying the radius of the spherical ball is increasing at a rate of 2 centimeters per second. So how can I put that into variables, the rate of radius increase? Nate, how can I write that? What is that?
DRDT.
That is DRDT. Two centimeters per minute. And they want to know at what rate is the surface area of the ball increasing when the radius is 8 centimeters. So what we have to do is now recall the next formula, which is the surface area of a sphere. So you would have to probably look that up to find the surface area of a sphere. And the surface area of a sphere is what? Anybody find it? Again. 4 pi r squared. Now, and this is just a side note to this. You have volume, which is 4/3 pi r cubed, which is 3-dimensional. Okay, area is a 2-dimensional concept, even though we're talking about a sphere. Area is 2-dimensional. If we take the derivative, not with respect to t, but take the derivative here, what we get is 4 pi r squared. So when you take your derivative, basically you're losing a dimension. You lose a dimension. You go from cubes down to squares, so you go from volume down to squares. So we get our formula down here. The next thing is to implicitly differentiate with respect to time. Here we didn't do it with respect to time. We just took the derivative with respect to our variable r there. If we take our derivative, we have s prime of our surface area. Our derivative comes down to what, Ozzy? Is equal to what? I'm sorry. Okay, so like when we have 4 pi times 2, we get what? 8 pi r, and then we have a dr dt. So they want to know how fast the surface area is changing. We know the radius is 8. And we know dr dt is 2 centimeters per minute. So we multiply these together, we get 6,428 pi centimeters squared per minute. Just looking at dimensions, centimeters, give me centimeters squared. have you do number 15? Is number 15 on there? All right, I wrote them down. That I had to change them back there. No, I didn't. Those are the problem that 3 through 7 and 13 through 16. All right. If we look at problem number 15, a street light is mounted at the top of a 15-foot pole. A man 6 feet tall walks away from the pole with a speed of 5 feet per second along a straight path. How fast is the tip of the shadow moving when he is 40 feet from the pole? So we have this light that's shining down, and we have this man that's walking away from the pole. And if we look at the idea and the concept of a shadow, it's the blockage of light creates a shadow. So if I would draw a straight line our shadow this would be our shadow here. We have a 15-foot tall pole that the light sits on top. We have a 6-foot tall man this is 6 foot tall. And we're looking at when he's 40 feet away from the pole. So if we say this distance here that he is away from the pole is x, and from here to here is s. The question is, what do we do with that 5 feet per second? What is that value? Well, that's the value. He's walking away from the pole. So how can I put that into my variable terms here? What would that value be? What variable is increasing at a rate of 5 feet per second? X. My x, as he's walking away here, is increasing. So this dx dt is increasing at 5 feet per second. You look at what variable is increasing as you're trying to figure out where do I put this. And what's increasing is the x is increasing. Well, what we have here is we have to create some sort of relationship between all the information we got here. Okay, well, when we had right triangles before, we pulled out our good old buddy Pythagoras. Well, we're really not looking at anything with respect to Pythagoras here. But what we do have is we have two triangles. We have a small triangle and we have a big triangle. And just like when we were dealing with a cone, we have a triangle within the triangle that shares a common angle. So if they share a common angle, and we're talking about heights of these two things. So we have a right angle here, and we have a right angle there, because we're talking about the height. So what we have here is we have a common angle, and we have a right angle. We have similar triangles again. And ratios of corresponding sides of similar triangles will be in proportion. Well, if we take a look at the ratios of the sides, okay, we have 6 and 15 that correspond because of the both heights. So we have 6, which is a small triangle, and then we have 15, which would go with the big triangle. Well, the small triangle will give us a value of S there. But in the big triangle, what value would we have to put down on the bottom? Ozzy? No. Okay, we're just writing a ratios of corresponding sides of these two triangles. So we have 6 to 15 is equal to S to what of the big triangle? Close. No. Brandon, what do we have to do with them?
You put 40 under it?
No, not 40, not yet. Adam? X plus S. X plus S. We have to get a general equation before we start throwing in numbers. Okay, before we start throwing in numbers, we have to get a general equation with just the variables. So now we can cross multiply. We diagonally multiply. Just using our properties of proportions. So we have 6 times X plus S is equal to 15 times S. So we have 6x plus 6s is equal to 15s. Now subtracting your 6s from both sides, we're left with 6x is equal to 9s. Now to me, I'm just going to look at it that way, because this way, and take my derivatives at this point. So if we implicitly differentiate with respect to time, both my exponents are a value of 1. So both my variables are going to go bye-bye. So we have 6 dx dt is equal to 9 ds dt. My dx dt is a value of 5. So we have 6 times 5 is equal to 9 times ds dt. We can divide both sides by 9. So we have 30 over 9, which is 10 over 3. So we have 10/3 feet per second, or 3 1/3. So it doesn't really matter how far you're away from the pole. At least in my calculations, you don't have to worry about it. Did I get it right, Dan?
There's 25
25 and a third.
feet per second.
25 and a third feet per second?
Yeah.
That's what they have? 25 and a third? $25 and a third.
They're asking how fast the tip of the shadow moving when he is 40 feet from the pole.
Okay, what I gave is the length of the shadow. How fast is the length of the shadow increasing? Maybe I solved for the wrong thing. The length of the shadow increases at 10/3. How fast is the tip of the shadow moving? Walks away from the pole. Speed 5 feet per second. I'm going to think about that one now. Not 25 thirds. 25
thirds, yeah.
Well, 25 thirds.
25 yeah.
So that would be 8 and a third. We have 3 and a third, and they have 8 and a third. I'm going to think about how to get the... Oh, there we go. There we go.
X plus DSDT is 10, is 3 and a third, and DXDT is 5.
Yeah. So they're both moving. So the length of the shadow is moving plus. Okay. There we go. That's better. Types of problems that you'll see as we continue to move forward. Ones that deal with similar triangles, ones that deal with right triangles and Pythagoras. Cone problems you'll see, and the spherical balls you'll see those types of problems as we continue to move forward. as we did with trig identities, it takes just some experience to go through and continue to work through problems. You just have to continue to put your head down and plow through the problems a little bit as you go through. Other questions that you have? What my goal was to spend, do a couple problems first half of class and then give you the rest of the time to work on the problems that are back there. There's 8 more additional problems. If we take a look at problem number 20, we'll sort of work through this together. You have a baseball diamond is a square with the side of 90 feet. A batter hits the ball and runs towards first base at a rate of 24 feet per second. At what rate is the distance from second base decreasing when he is halfway to first base? So we got a rectangle or a square. And he's running towards first base. And we're 90 feet. There to get to first base. And we want to know the distance when he's halfway at 45 feet. This distance to second base, how fast is it decreasing? Well, if we take a look at this relationship here, and we throw it from not that he's running away from home plate, but he's running towards first base. So let's let this equal our x value. And this distance to second base is equal to d. The distance from first to second base is still 90 feet. Well, what we have created here is we have created a right triangle. And if we have a right triangle, we have our good old buddy Pythagoras. The key to this is to get the right triangle going in the right direction. Rather than coming from home plate towards first, we're going from where the position is at to first base. He is running down first base to first base going at 24 feet per second. Okay, so this goes to our x, but what do we have to put with that 24 feet per second? Okay, it's going to be a dx dt. But what is happening to this distance x here as he continues to run down the base? Is it getting bigger or getting smaller? Evan? It's getting smaller. So what do you think we should throw with the 24? A negative. So we should throw a negative there. Why? Because it's getting shorter. Okay, now we have our good old buddy Pythagoras. We can write an equation. The 90 feet from first to second base is not going to change. That's going to be a constant. Nobody's moving the bases as we are running. So that's going to be 90 feet. So write yourself a Pythagorean equation that involves x, d, and we're looking at the distance to, bless you, our distance, bless you, square it, our distance from the runner here to second base. So we're looking at this distance, so what would be the Pythagorean equation? Okay, now take the implicit differentiation of this, implicitly differentiate. The derivative of 90 squared, 0, because it's a constant. So we have 2x dx dt is equal to 2d dd dt. If we wanted to, we can simplify things. We can divide 2 out of both the sides. They would cancel away. So we have x dx dt is equal to d dd dt. We know x is 45 because he's halfway down the line, so this is 45. So we have 90 and we have 45. What we have to find is we have to find what d is. So what's our distance d using our Pythagorean equation? When this is 45, what's d? So we have 45 squared plus 90 squared is equal to d squared, and we can take the square root. Adam, what do you get for d?
100.62 feet.
100.62 feet. And then we can substitute in. We have 45 times 24, negative 24 feet per second is equal to d, which is 100.62 feet dd dt. So we take the 45 times the negative 24 divided by the answer that we just got. Bailey, what did it come down to? Feet per second. Now, when you do the second part, now we're going to third base. We are going to third base with this. So our right triangle now includes home plate, where the runner's at, and third base. So my dxdt, what's happening, my x, I can throw my x here now. So what is happening to x now? It's increasing, so it's a plus 24 feet per second, because now x is getting bigger. He's running away. But it's the same type of principle. You can put any variable you want in here. I still have 90 feet here. So I can use my Pythagorean equation and set up and solve it the same way. Now the question is, you have to solve for y. Is y going to be the 100.62? You have to solve for that. All right, rest of the time I'm going to give to you. We'll go through one more type of problem tomorrow. We'll sort of work together on a problem.